Okay, Colin, I'm going to explain the math I see. I might not say all the science words right, but here we go. So in this first part, it's saying that these three things, A, I, P, that I reaches a steady state. So a steady state, they probably mean like a constant. And remember, if you have a constant, the derivative of a constant is zero. So that's a thing to know. So a constant is, no increase, no decrease. So it's basically like a flat line, right? We already know that the concentration of A changes and they give, basically, I guess they give you this formula. So like this is a formula I guess they gave you previously for A, right? The initial value of A times e to the negative whatever K1 is times the time, okay? So I guess that was given to you before. All right, so then it says products are formed exclusively by unimolecular decay of I. So the rate law for that step is this. So they are doing the derivative of P with respect to time. So they're trying to find the rate of change of P, whatever, I don't know what P is, but over time. So they're basically doing the derivative of P, right? So they're saying that this is equal to K2 times I. So remember that's a constant though, because I is in a steady state, so it's a constant. So multiplied by K, which I assume is just some other constant. So basically it's going to be a scalar, or a scalar times I, all right? So the question again is how to calculate I. So I guess I is not a constant necessarily, okay? But eventually it will be. All right. So because I reaches a steady state, we can introduce the steady state formalism, right? When a substance reaches a steady state, we assume that its concentration does not change in the time appreciably. So that's what that means, right? Like there's no change. So your derivative is equal to zero, right? So like the change over time of your species is zero. So basically you have like a flatness if you were going to graph this thing, right? So in order for the concentration of I to be constant on time, the rate of the process that forms I has to be equal to the rate of the processes that remove I. All right, so basically they're saying they know they cancel each other out, right? So they're saying that the rate, when you subtract the two, has to be zero, because you know the rate is equal to zero. And so when you take your two versions of with I and A there, you know your derivative is zero. All right. So anyway, so they know that that's equal to that, and they know that, and then this is equal to that. So basically, they're just like knocking this out and saying this is equal to zero, which means these are equal to each other. Okay. So that's how they're solving for I, because earlier they said they wanted to get I, right? And so they know that I is K1 over K2 times A. Well, A was given to you earlier, right? You had that formula for A. So basically they're substituting this information in for A down here. Oops, for A down here. Okay, so that's how they're getting this formula there. All right, so notice that the expression for the concentration of intermediate I under the steady state approximation is far easier than the one seen without approximations in equation 9.1, I guess on the page before. More importantly, because now we have an expression for I, we can proceed to solve for P. So, so earlier you found out that the derivative of P was K2 times I, all right? So now that you know what I is, oh good Lord. So I think what we're gonna do the next page, or that thing, they're gonna multiply K2 times I. So if you multiply, this is I, if you multiply it by K2, that K2 is going to go away, right? So I think that's what we're going to see on the next page. And they're saying that the derivative of P is equal to this. So to undo a derivative, you take the integral. And so that's why we're about to do the integral. Okay, so here. So they've made all this substitutions like I was saying. This canceled out. And if we do the derivative of the, if you do, yeah, this was just what they had earlier. That was that. They're putting this over here. So the derivative of P is equal to here. So what they're doing is they're doing the integral of both sides, right? And so when you do the integral of a derivative, then that means that P is going to pop out, right? Because you're undoing a derivative. They're the inverse operation of each other. So now we have to figure out the integral of this, which turns into that. So and it basically turns into that. So we are going to do the integral of this. That's what we're about to do down here. All right, so we got these two, K1 and A0. Those are just, that's your initial value of A, and K1 is some constant from before. So those can come out front, right? They can come out front, they're constants. And so basically you have the integral of this left to do, right? So that's e to a power. So let me remind you, when you do the integral of e to a power, you have to use u substitution. Now you can get better at it and just do it in your head, but what you learned in calculus is you're going to make this equal to u, right? Then you do the derivative. So because the integral of e to the x is just e to the x. So I have to get that situation so I can use that rule. So I move the 5 over here, so I'm going to substitute now. So dx, this dx is replaceable with 1/5 and du. That's what this says right here. And then over here, u is 5x, so that's where I'm putting u. So everything's in terms of u now, but you get this extra little constant out front, this multiplier. All right, so when you do the integral of e to the u, it's e to the u. The 1/5 follows u, and then you just put your u back. Because really, remember that you want the derivative of this to be that. So if I did the derivative of e to the 5x, it would be e to the 5x times 5. And see, these 5's cancel, getting me back to here. So this is right here is just counteracting the derivative of this part here. Okay, so, and as you get better at it, you're like, oh, integral of e to the 3x. Oh, well, that's just 1/3 e to the 3x, right? You just have to counteract the derivative of the 3x. All right, so what you have in your problem is this. Here's your power. So that's your u, and this is just a constant. So you kind of know by my rule here, I'm going to get 1 over negative k1 as my multiplier out here, right? So I do my derivative of this part, I get negative k1 dt. I move this underneath over here, so I am replacing dt with 1 over negative k1 and du. And then u is now this, so that's why I put u there. So integral of e to the u is e to the u. That just stays along. And then it's still there. I put my u back, and I'm done. Now, we're not going to have to put plus c because there are numbers on this thing. So let me just follow that through. So the numbers on this thing are going to be 0 and t. Okay? So that means I'm going to leave the 1 over negative k1 out here, and I'm going to plug t into this, right? So I get e to the negative k1 times t, minus, I got to plug in 0. So if I plug 0 into here, e to the 0 is 1. Okay, and so that's what I'm going to pick up on the next page. All right, or on the rest of the page. So we were here, and here's where I just was. So out front here, so did you notice earlier when I did my integral right here, the answer for my integral was, if you remember, it was 1 over negative k1 times all that, all right, or times that stuff right there. All right, so that fraction I had out front is under here, but remember, this problem also has these pieces. So look, if those pieces, and you have a division by negative k1, look at those k1s, they go away. So I still have a negative a0, all right? And then I went and put those values in, just like I did on the last page, and I got here. So we're now to here. But that k1 has disappeared because of these other things that were already in my problem. See, I was putting the negative k1 under that, and they went away. All right, so now I'm here. Well, this negative sign, if you put this negative sign to this part right here, they can just basically like switch places, right? Because this becomes negative, that becomes positive, and that way you don't have to put your negative sign there. All right, so there you are, and that's why that is the answer to that integral. Okay, and this was like your little differential equations right here, because they were splitting. They basically had dp dt equals something, so they moved the dt over to this side, and then you can integrate both sides, and this side becomes p, and the integral of that is basically going to become your answer, and so you're going to get that equal to p. So I guess they were trying to find p for some reason, and that's why. All right, hope that helped, and I'll talk to you tonight. Bye-bye.